The beginning of public water supply. It was over 200 years ago. The textile industry flourished during the Age of Discovery and the Industrial Revolution. In 1804, in Scotland, UK, Gibb was inspired by spring water from a riverbank and created clean water by running stones and sand to the side to wash away dyes used to dye textiles. He had some left over after using it in his own factory, so he sold it around the city. This is said to be the beginning of public water supply. During the Industrial Revolution, many people concentrated in cities and urban rivers became polluted. Simpson was hired by the Chelsea Water Company in London at the age of 24. He worked for the Quest for Pure Water across the UK. At the age of 28, he made clean water from the polluted River Thames in London by settling it and then running it through a sand filter from top to bottom. He called it a sand filter because clean water can be made by filtering it slowly through sand. Later, at the age of 30, he built a practical filter measuring 100 mx 40 m in 1829. It became popular that the polluted water of the Thames could be made free of pathogens by using a slow sand filter. This English filter spread all over the world. Simpson's filter was shallow, at 38 centimeters, and the filter rate was slow, at 10 centimeters per hour. The filtration rate that spread throughout the world was 20 centimeters per hour, or 4.8 meters per day. At the age of 39, Simpson said that the filter had more removal capacity than a mere mechanical filter. Perhaps he felt that living things were involved. The effectiveness of slow sand filters became clear in 1892, when a cholera epidemic broke out in Hamburg, Germany. When the water was filtered, the cholera bacteria were removed. Robert Koch investigated the number of bacteria in tap water. He reported that if there were less than 100 general bacteria in 1 milliliter of water, it was safe against cholera and typhoid. This idea and numbers are still used in the current WHO tap water standards. There was no need to make it sterile. The idea was that it was enough to reduce the risk. A report from Berlin, Germany in 1893 stated that dirt only occurred on the top of the sand layer of slow sand filters, and that this dirt was related to temperature and sunlight. It was pointed out that it was related to biological phenomena. However, it also said that the fine sand likely caused the main removal of dirt mechanically. However, when you compare the size of bacteria to the size of sand, it is difficult to explain that they can be removed mechanically. The slow sand filter was also introduced to the New World, America. Winter temperatures in North America are low, and biological activity is low. In the past, clear filter tanks were not covered because slow filtering could remove pathogens. Rivers in the New World were less polluted by farmland and cities. This was because there was less food for living creatures. Also, the water temperature was low in winter, making it difficult for living creatures to thrive, and the filters in the rivers quickly became clogged due to turbidity. So chemical treatments were developed to combat turbidity. However, the filters quickly became clogged, so they were backwashed. This treatment allowed bacteria to pass through, so it was necessary to disinfect the water with chlorine at the end. Chemical treatments did not remove the odor and the filters quickly became clogged. To avoid the living organisms, algicides were used. It was pointed out that chemical treatments could produce carcinogens, and in 1974 the WHO published a manual of slow sand filtration that did not use chemicals. A large-scale outbreak of diarrhea occurred in a rapid sand filtration system with a backwash process due to cryptozoa parasites that could not be killed by chlorine. Rediscovery of slow sand filtration has begun around the world. As a chemical-free measure against turbid water, upflow roughing filtration was studied in Brazil in 1980. The first international conference on slow sand filters was held in London in 1988, where Bernardo from Brazil made a presentation. Wegelin from Switzerland also researched past roughing filtration and made a presentation. International joint research was then conducted, and a manual on roughing filtration was published in Switzerland in 1996. I obtained the roughing filtration manual and conducted experiments in buckets and pilot plant tests. The sludge from upflow roughing filtration was similar to activated sludge from sewage treatment. I found that the main role of the biological community in upflow roughing filtration was to capture and decompose turbidity. In the slow sand filter, algae grow in shallow water on the sand surface. Microorganisms are active near the surface of the sand layer. The area near the surface of the sand layer is where the microorganisms find food. The microorganisms desperately grab hold of the turbidity and excrete it as fecal pellets. There is no oxygen left in the fecal pellets, and decomposition is progressing through fermentation. The reason that temperature and sunlight are related is because of the activity of living organisms. Algae produce oxygen through photosynthesis, creating an environment that is conducive to the activity of microorganisms. There were many tiny organisms active there that could only be seen under a microscope. These organisms were active near the surface of the sand layer where food came from. There, a food chain of eating and being eaten took place, and they thoroughly decomposed all kinds of substances. Chironomid is not same as mosquito. Chironomid larvae making nest at the bottom. These environment with current have dissolved oxygen. Mosquito larvae live in stagnant water. The mosquito larvae float on the water surface, drifting with their tails up. Their tails act as respiratory organs. Chironomid is called non-biting mosquito. In an environment with currents, filamentous algae grow. Protozoa are also active among the algae. The yellow grid is spaced 1 mm apart, so you can get an idea of the size. There are also nematodes, organisms without mouths that absorb substances through the surface of their bodies and take them into their bodies. There are also the larvae of aquatic midges. Animals eat anything that fits in their mouths. The filamentous diatom Melicera is an excellent food for the larvae of aquatic insects, midges. Chironomids live on the sand surface and just below the sand surface. They breathe through gills. Hungry animals will eat anything. It is important that hungry animals can live in peace. Chironomid larvae make nests on the surface of the sand layer of the filter pond. They move around in search of food. They come out of their nests to eat food. If there are many chironomid larvae, clogging is less likely to occur. The food eaten is not completely broken down in the chironomid's intestines and is excreted as fecal pellets. Decomposition continues in the fecal pellets. Mosquito larvae live near the surface of still water. The mating behavior of both insects is similar, so they are easily mistaken. Chironomids are called non-biting mosquitoes. The slow sand filter was named after the mechanical sieving of fine sand. The key to purification was the work of algae and microscopic animals. Algae produced oxygen, creating an environment in which animals could thrive. The top-down flow did not move the sand, creating a friendly environment for living things. Slow meant being gentle to living things. Slow sand filtration, which was completed in London, England, 200 years ago, spread throughout the world because it was able to remove pathogens. The purification mechanism was a food chain of microorganisms. In Japan, it was said that the purification mechanism would be misunderstood if it was not called an ecological purification system, EPS, instead of a slow sand filtration. This idea led to the development of a new structure and maintenance method. EPS has begun to spread from Japan to the rest of the world.